So ladies and gentlemen, as software-defined vehicles evolve, AI is increasingly moving from the cloud to the edge. So what does that mean for future vehicle architectures? What does it mean for performance? And what does it mean for efficiency? Well, let's find that out. Yesterday, it was a bit more about like we are entering the edge of AI-defined vehicles, and now we would like to dive deeper right now into that topic and hear about computing power that enables edge AI with all its implications. The next speaker came all the way from Texas to AEK 2026 to find some answers together with you. And again, we are happy to have a Q&A afterwards, so place your questions for Dr. Ahmad Bahai, the Senior Vice President and CTO of Texas Instruments and professor at the MIT.
Good morning. It's my pleasure to present at the 30th anniversary of AEK. There is a lot of exciting technology improvements and technology opportunities happening, and I'd like to highlight, as a semiconductor company, first what's happening in the semiconductor industry, which is quite compelling. Almost every aspect and every market in semiconductor is growing, and the most conservative forecast we had in semiconductor is that by 2030, it's going to be a $1 trillion market. In fact, it's happening this year. And that shows how fast semiconductor all of a sudden is accelerating, and the data economy is driving semiconductor in every aspect of it. People talk about AI quite a bit. The concept of AI started in 1950s. Actually, the first lab at MIT on AI started 1950s. And the reason that we see AI is growing so fast is partly because of the semiconductor innovation that has created that opportunity and every aspect of it. What I wanted to highlight is that when we talk about semiconductor, it's not just the scaling at CMOS level, but also we see many new materials and many new devices are coming up, very innovative devices that can change the picture of the semiconductor industry significantly. Things that really relates to power or photonics or analog and RF, and a wide range of sensor technologies are not just relying about the scaling of the CMOS, but also new materials. I mean, things like gallium nitride or gallium arsenide that we knew in the past, but also MEMS technologies that's really enabling a lot of new sensing modalities, and also power management, which is becoming a big bottleneck in a lot of these AI applications. Also, we see opportunities on quantum computing and many others that we don't have time to talk about, but it's an exciting time to see that a single direction of innovation now is expanding to multi-dimensional innovation in semiconductor. Here's a chart that I wanted to get your attention to that, because it shows that the scaling at package level is now accelerating faster than the scaling at transistor level. And that is a good preamble to what's happening in the chiplet, because there is a lot to achieve there as long as we can maintain the cost effectiveness of these integrations. So with that introduction, I'd like to highlight the fact that we are at the era that machine learning and AI is impacting every aspect of our life. Even the search that you are doing today is no longer just a simple search. It's a highly AI-enabled search, and all the way to autonomous systems and robotics and everything that you heard about. So when did that revolution happen? Really happened around 2017, 2018, when all of a sudden we came up with this concept of generative AI. The basic concept of AI started many decades ago, but generative AI, the fact that you can have a different angle to AI, completely changed the picture. And from that point on, we see what we are talking about as federated learning, and that's very important for automotive also. Federated learning means that you can learn at the cloud because you have the ultimate resources, but also you ripple through this learning across different stages of the computing. And that's very important because it's not just the intelligence, but also learning and training that needs to be distributed across for many reasons that I'm going to talk about shortly. So we talked about vehicle architecture, and OEMs are a lot more knowledgeable how this vehicle architecture is evolving, and we heard about that. But clearly the message is that the distributed domain architecture is moving toward this central zone architecture. So what does that mean from semiconductor angle? High performance computing is becoming a really key factor. Now, call it SoC or you call it a chiplet integration. There are variations of that. But whenever I talk about chiplet, we need to distinguish from chiplet of the highly scaled CMOS versus chiplet in analog and mixed signal. Totally different implications and totally different set of challenges. The other thing is federated learning. Where does that learning happens? Training and learning and intelligence. Of course, when you're at the cloud level, you have ultimate access to the processing resources as well as data, but then the latency and security and many other topics come to the picture. Sensors and edge AI, how much of the intelligence needs to be coexist or reside at the sensor level? And you heard some of that earlier in the morning from the speakers. I think that is a very critical factor in defining the sensor intelligence. And networking, of course, when you have this new architecture, that means massive amount of raw data are going to flow across this network. So you need to get higher bandwidth on the Ethernet. And on top of that, timing, because a lot of these high-performance devices need to talk to each other in a synchronous way, and then timing becomes a critical factor, or timing references. In Texas Instruments, we work on all these aspects of it. We strongly believe that the future of semiconductor is going to be even more exciting. That's why we have put together 4 300-millimeter fabs in the US, 2 in Texas and Utah, and more are coming online. One of the largest semiconductor manufacturing capabilities in the world, because we believe a lot of these applications are going to ask for more and more semiconductor technologies across the board. So let me start from these 3 steps of sensing, processing, and interacting. Sensors are becoming more intelligent and more accurate and higher performance. But to get maximum performance out of these sensors, you need to make sure that there is enough intelligence residing with the sensor. And these are microcontrollers with AI capabilities, or we call it embedded AI. Could be RISC, could be sub-RISC, because in some cases it has to be, in fact, we announced 1 millimeter by 1 millimeter microcontroller, including AI processor, for applications that you need to really take the data at the sensor level and clean it up before sending it to the next level of processor. Also, the low latency of the processing and privacy and scalability are important factors to define the architecture and making sure that we have the right level of the learning and right level of intelligence across different layers of the processing in the system. So this concept of sense, process, interact constantly is getting more and more challenging. I mean, the number of cameras, the number of radars, the number of LiDARs. I mean, for those of you who have been in San Francisco lately, and look at these autonomous robotaxis, it's quite impressive. I mean, when I used it, 2 years ago I was nervous to use it, but now I'm using it every time I'm in San Francisco. And the number of LiDARs and radars around the car is amazing. And the accuracy, the intelligence of the car is quite impressive. So you see that as we move forward, this amazing amount of data and sensor intelligence needs to be managed in a very creative ways. Of course, for many ADAS or IVI applications, you need to get access to this raw data. But for many applications, you need to make local decisions. Or maybe in some cases, you need to make local signal processing and local, even in some cases, what we call it embedded partial training. This concept of embedded partial training still is at the early stage of infancy. But the idea is that sensors, depending on the mode of operation and where they are installed and what conditions they are exposed to, may need to improve their learning, and that needs to be in a federated way. You cannot just send the whole thing to the cloud because it's not a common thing for all sensors around vehicle or even in other industries. That's why we are working on the concept of federated learning as one of the opportunities to make the system more efficient, make the system more secure, and offer opportunities to improve the quality of the overall system without a big penalty on the power or bandwidth requirements. So here's an example of that. The radar is becoming one of the most common sensing in the cars, and we see a wide range of radars. I mean, from basic proximity sensing and in-cabin applications, all the way to cascaded imaging. And you see that the performance requirements, orders of magnitude, varies from different applications we have. As you can see in this picture, we are dealing from 500 MIPS, or mega operation per second, all the way to 37 giga operation per second, depending on what you're doing with this data. And accordingly, if you want to pass this data across different domains, first of all, you need to synchronize them. Second, you have to have a link to manage this amount of data. In fact, we worked on this technology called dielectric waveguides as an opportunity to kind of pass these data across different radar, distributed cascaded radar systems, to make sure that we can offer the highest bandwidth at the lowest power. I mean, a lot of applications are getting to the point that this collaborative signal processing is very critical. Now, in the past, some applications required local AI for these radars. Now the idea is that how to pass the raw data to the central processor for ADAS, and that means a heavy toll on the bandwidth of the network. As I point out later, there are some creative ways of, in fact, we talked to some major car companies in US and Europe and in China, and see that, people are getting really creative on to offer how this higher bandwidth, and I'll talk about that in my next slides. Another great example of that is LiDAR. Not every OEM takes LiDAR as the next option, but we think that LiDAR in many applications or many scenarios could be an addition or complementary sensing modalities. We developed a technology in TI many decades ago that is quite exciting. We put about 2 million meters on a single chip. You heard it right, meters, not gates. I mean, so these meters on a single chip have the lifetime of tens of billions of switch flipping without any reliability issues. In fact, if you go to a movie theater, I don't know how many people go to movie theater these days, but go to movie theater, 98% of projectors are based on DLP multi-million mirror systems. The idea is that you have a couple of million mirrors on a chip, and now you can steer the light the way you want. Pretty much for display, what you do is that you control the pixels and you shine the light at the right pixel. But what if we can use the same concept for LiDAR? Because LiDAR, one of the key problems with LiDAR is cost and reliability. So people came up with semiconductor version of the LiDAR on silicon photonics. Still, reliability is a big issue because of this thermal management. We think we can use this massive amount of mirrors to steer the light with minimum number of the diodes, laser diodes, meaning that reducing the cost significantly, both on the transmit and receive. So again, it's another example of semiconductor innovation, which took us a long time to make these mirrors flipping for billions of times without extinction. And now we can leverage that to offer a beam steering capabilities on the optical front. And we are thinking of using this for many applications, including optical switching and potentially bringing LiDAR to the next level of affordability. One of the missions of the semiconductor industry is that through ultimate innovations make things a lot more affordable so they can expand the market significantly. So these are some of the examples of how sensing can change the whole picture of the architecture, intelligence, and data transfer. So let's talk about opportunities at the edge. Let me split the edge in two segments. One is the edge, and the other one is extreme edge. What I mean by edge is that if you look at your laptop today, we can call it as edge computing. It has a lot of intelligence. In fact, many new laptops, including the ones that you're looking at right now, maybe it has a couple of GPUs built into that, because a lot of intelligence is happening at that level. And there is extreme edge, which is the intelligence at the tiny sensor that is running off of a very small battery or is low power or low form factor and die size. And we need to separate that. But the beauty of the federated AI is that you split the intelligence accordingly to achieve the performance that you need in the system. And the hardware needs to support that. And I'll expand on that on my next slide. But the key factors is that power consumption is an issue, security and privacy. As one of the speakers mentioned, safety and reliability. Of course, the latency is becoming very important. In many applications, you can't afford to have everything centralized if the latency is beyond what you can afford and accept. Throughput, which really is kind of like the bottleneck of the communication. And of course, last but not least, is affordability. And all of them come to the picture on how to split these things. And when you talk to different OEMs, different visions, different architectural preferences, a lot of pros and cons for many, but it's all exciting and a lot more aggressive than what we see what we saw a few years ago. So let me give you an example of how we handle this edge AI in a most efficient way. So on the left side of this thing, I wanted to compare cloud AI versus edge AI. So both techniques are heavily relying on cloud. But cloud is, in this point, in many cases, a training platform, meaning that you may use large language models, or in many cases now people are talking about LRM, large reasoning models, which is a lot more efficient, but that is cloud issue. So we have this massive amount of data, and we need to have this massive amount of processing. And with that, we can offer this large language model kind of training of the neural network algorithms that we wanted to implement. And then once we have those trained, we put it in an embedded condition, meaning that now you have a real-time AI that is handling with the real-time data based on neural network models that we have. However, as you are experimenting that in your car or any other industry, you're gathering more data. So how much of this new data needs to be passed to the cloud or processed locally? That's a big debate. Some of my co-workers, AI experts and AI companies, thinking about how to do this additional real-time learning in a more creative way so that we don't need to send everything to cloud. So think of it like this way. If you download an LLM model from the cloud, tomorrow that model is outdated because now there is new data on the cloud. So the question is that, should I send everything to cloud or should I do some of the learning? And that federated learning, what is the level of the learning, is very important optimization of the power, latency, and privacy, and maybe your competitiveness. And we have been working on platforms that support different architectures because we are not going to decide about that. The OEMs are going to decide. But that is where we see that semiconductor platform needs to support that. So what you see on the right-hand side is our Edge AI MCU that can scale from sub-RISC, meaning that the cores that are much smaller than a RISC-V, with an AI accelerator in hardware. So you can decide how much of this AI algorithm needs to be done in software versus AI accelerator. And by the way, the chip size, the tiniest one, and for obvious reason, we call it tiny engine. It's about 1/4 millimeter by 1/4 millimeter, and includes the AI hardware accelerator and security accelerator, because security is becoming more critical on every of the applications. And we see that now the user can decide how much of the AI algorithm needs to be done in software versus hardware. But here is another piece. We call it real-time edge AI partial training. And that's the part that when you want to do this training, okay, training goes on up the cloud, but then you can do federated learning, meaning that when you capture more data, which is unique to your sensor, because of this mechanical or any other unique characteristics, you can go to the cloud and find the sensors that experience the same kind of characteristics, and then have the partial training so that you reduce the latency, but at the same time you can benefit from the set of data that is available at the cloud. So the Tiny Engine NPU is the most power-efficient AI and security accelerator that we are including in not only our small cores, but also bigger cores like C2000 and all the way to some of the advanced DSPs. And it's highly scalable architecture, and it's a multi-tile architecture. So depending on how much processing you need, you can scale it accordingly. And the tools that we are offering is that really simplifies the translation of the algorithm to the most effective or most efficient implementation of the AI on the hardware, almost transparent to the user. So you can go to the tool, define your algorithm, it searches for the right neural network library, and once you have the right network library, you can train it, and after training, You can embed it in your core processor and then do partial training as needed also, without writing a single line of code. And that's the power of AI. That's why they're saying that these days the coding skill for entry level is becoming more and more difficult because AI is obviating a lot of these opportunities, and we think that's just the beginning. On the high-performance compute, of course, the high-performance compute is driven by data centers. They are pushing the limits on that one, and obviously a lot of semiconductor fabs are focusing on sub-5 nanometer because they see that the opportunities for big market and big applications are there. But also we see that the same kind of, some of the challenges are going to be in the central compute requirements of the automotive. So potentially we have multiple tools at our disposal. We can go through this 2.5D or 3D integration. This is mainly for high bandwidth memory and main processor. We can work on chiplets because these SoCs, development of these SoCs are very, very time-consuming and resource-consuming. Just to give you an idea, a typical SoC for the latest data center costs hundreds of millions of dollars to develop, a single SoC. So obviously, having the concept of chiplet, and in some cases heterogeneous integration, because you need to integrate at different levels, and AI accelerators are critical. But also for the same reason, power management. Some of these processors consume more than 1.5 kilowatt per processor. So you have to deliver, I mean, now we're talking about 2 kilowatt and beyond. So massive amount of power needs to be supplied to these processors. And there is a lot of interesting innovations that semiconductor companies are doing, including us, on backside power delivery, IVR, integrated passives, thermal managements, and how to use these advanced materials like gallium nitride to improve the power delivery. And high-speed interconnect is another important thing, chip-to-chip, module-to-module, and across the network. And another angle that is very interesting in data centers in automotive, these low jitter timing references are becoming very important. A typical data center's clock reference requires something around 20 femtosecond type of jitter, which is extremely challenging, and we are very excited to use some of our MEMS devices to provide that. But also we see that some of these timing requirements translates to opportunities in automotive. Networking. We heard about networking. When you go from the distributed architecture to decentralized, higher data rate, higher resolution of the sensors, number of sensors are growing. So all of a sudden we see that some of the OEMs talk about the same exciting idea that is happening in data centers. They are talking about silicon photonics. They're talking about optical networks. Some of the things that is new, but or maybe coming to automotive again, but we see that in data centers now they talk about the scale up and the scale out. So we see the similarities in many of these technologies are quite staggering. It's amazing to see that in the future, we are talking about 10 cents per gigabit per second for optical links. That is the best you can get. I mean, today is about sub-dollar, but you can see these innovations are happening in that front, and innovations in one area is rippling through the other markets and opportunities. Of course, on optical, as you know very well, you get other benefits like EMI immunity and low-cost cables and many others. Of course, cable itself in automotive has other challenges too. So, as I said, timing is very interesting for us, and that's why we came up with a MEMS-based timing reference compared to crystal-based, and we think that we can offer significantly higher jitter performance in the orders of tens of femtoseconds compared to any other timing references. And this is going to be critical because some OEMs are talking about how to synchronize data packets across different nodes of the network in the car. And also we see that as an opportunity for more innovation across different disciplines in automotive. So with that, I'd like to thank you for your attention and be happy to answer any questions if there is any.
Thank you so much.
Thank you.
So that was really a deep dive, and I think we have, again, lots of discussions that we are provoking during the coffee break. We have directly a question from the audience that I would like to place here. How do you look at risk 5 and collaboration in open source? Does TI think about contributing to Eclipse S-Core?
Yes, actually we are very open to all these open source opportunities because we think that the collaboration across the industry is very critical for innovation and for adoption. As I mentioned in my talk, many of the innovations that happening in the data centers and other segments of the market can also impact automotive quite readily and quite impactful. So the answer would be yes, we are heavily involved in all of these open source architectures, and we support that.
So to summarize your presentation, the future of SDVs is not a single supercomputer on wheels. It is more like a disrupted intelligence system with centralized compute and decentralized intelligence?
Yes, of course, the architecture needs to address many aspects from cost to efficiency to reliability, security, safety, and others. But we think in the future, the intelligence is going to be federated across different levels. I mean, if you need to have, let's say, my simple example is that if there are issues that are related to the specific sensor that needs to be addressed locally, is most efficient to address locally. Things that needs to be fusion of multiple sensors and it needs to be handled centrally, then you do it in the big SoC. So it's really, we think that this intelligence needs to be available and addressed at every level, from extreme edge to central. That's why these microcontrollers or these processors that we have need to have this element of AI acceleration as needed. And that's why in almost every family of processors, we are thinking of having this capability for applications that demand this federated learning.
This is a really good point. Let's come to this later. Another core topic of your presentation was the energy efficiency, and we have a question from the audience here. Would you mind to read it by yourself? Downside, it's loss of energy wasted. What are your ideas towards low power silicon with a massive power consumption?
Yeah.
Will have rising impact on energy consumption.
Okay, that's a very good point because, again, ideally, if you want to, this concept of central versus distributed is not specific to automotive. Almost every industry talking about, okay, how much intelligence you need on your laptop versus how much intelligence you need on the data center. So this debate is going across industry. And I don't think it's a black and white decision. It really depends. As I said, if you can benefit from centralization, meaning that you need to get access to raw data to combine it to offer a better ADAS or IVI, you have to do it, and you pay the penalty of the power and bandwidth and all that additional cost. But if in cases you need to handle the intelligence locally and it doesn't benefit from central aspects of it, then what's the reason for doing that, to pay that cost that the question is addressing? And I strongly believe that, and that's why it's interesting that when we talk to different OEMs, a different vision on how much of it should be central, how much of it should be distributed. And of course, we are supporting all of those philosophies, but logically, power, bandwidth, complexity, cost defines how you use this federated latency. Clearly, we see that we need to have intelligence presence from the extreme edge all the way to central processor.
Good point. Sending huge raw data, hundreds of GBs, to cloud has a cost. What's the right balance? It's another question from the audience. Thank you for that.
I'm sorry, can you repeat again?
Sending huge raw data and so on to cloud has a cost. So cloud costs money.
As far as I can tell, very few, as far as I can tell, as again, I'm not an OEM representative in any ways, I don't think people are talking about raw data to the cloud, because a car is going to be a kind of a small data center on wheels. So we're talking about raw data to the central SoC on the car, and then some other level of the interaction with the cloud. the point is that many car companies that are using these autonomous driving features more and more, especially in US, and I'm sure they are very proud of the amount of data they have collected. They call it 100 million hours of driving or whatever it is, because that data that they are using or collecting helps them to improve the experience for the users and drivers. But in most cases, I don't think they're sending the raw data to the cloud. There's a lot of local processing, and the data to the cloud is going through different levels of the granularity of the data.
Mm-hmm. Thank you very much. And we have another question. We have lots of questions, for telling the truth, but due to our time, and we have the coffee break.
Sure.
In front of us. So, well, how does Texas Instruments implement AI on SoC architecture level? This is also a really good one.
So, TI is not working on data center SoCs because we are not into 2 nanometer, 5 nanometer type of big processors. These are like multi-100 billion gates processors. As you know, there are a couple of companies driving that. Our focus is mainly on the processors that are either at the edge or DSPs that are really much more power efficient than a big processor in terms of the joules per MIPS. So we are actively involved in every aspect of it, but we are not doing these giant GPUs that are multi-billion gates, because that requires massive digital, and our focus is to be the largest or the leading analog mixed signal company in the world.
Mm-hmm. So the coffee break is ahead. We have more questions here. Oh, still more questions coming in. Yeah. So may I ask Alfred, so will we? Okay, so the chef told me to quit here, but discussions, of course, go on during the coffee break. Thank you so much for your time. Thank you. Your applause.
Thank you.